How can a satellite's orbit be determined with radar readings? And how can the location of the satellite be calculated when it's not in sight? In this video, I'll be walking through my orbital propagation project, where I do just that. I will use radar readings to predict where a satellite will be after 72 hours, and compare my results to NASA's high-fidelity mission analysis tool. This was my computer project for Georgia Tech's AE 3330. A fictional satellite named HyperSat is being tracked by Peterson Air Force Base when there's a malfunction in the radar system. All contact is lost, but the last reading is at my disposal to assess the location of the satellite. After 72 hours, it comes back online. Where does a radar need to point to find the satellite? My objectives are to first determine the initial orbit by converting radar observations into Earth-centered inertial position and velocity vectors. Next, I must compute the orbital elements from the given initial state. I will then solve Kepler's problem to predict the future position of the satellite 72 hours later. Lastly, I will evaluate the accuracy of my results by solving the same problem using NASA's GMAT software. Determining the initial conditions was broken into two steps. First, I converted the radar readings from DU and TU to kilometers and seconds. Next, I converted the coordinate system from topocentric to Earth-centered. I would like to include my MATLAB code, but since this project may be assigned to students in the future, sharing it would violate academic integrity. Therefore, I will only be presenting my results. The given initial conditions were used to calculate the classical orbital elements. First, the specific angular momentum vector, node vector, and eccentricity vector were found. With those, the rest of the orbital elements could be derived. Kepler's problem was solved iteratively until the error found was less than 10 to the negative 6th. This returned a value for the true anomaly after 72 hours. This was then used to calculate the position and velocity, reaching a final answer. The General Mission Analysis Tool, also known as GMAT, is a software developed by NASA to compute a wide variety of spaceflight missions. GMAT is free, open source, and can be learned with built-in tutorials. I used the initial conditions of HyperSat to simulate the orbit in GMAT and propagate it 72 hours. These were the results. Comparing the results found with MATLAB versus the high-fidelity results found with GMAT shows that while manual calculations were done correctly and rendered approximate results, there's still a significant margin of error, with the worst position error being 0.66%, or 120 kilometers off. This error is likely due to a lack of considerations of other variables that are taken into account by GMAT. This includes the gravity of the sun and moon, solar radiation, and atmospheric drag. In conclusion, solving orbit propagation problems with classic orbital parameters is a viable method for low-fidelity preliminary analysis. Although, with this being said, when precision is needed in development for satellite trajectories, further considerations must be made. Thank you for watching.